Thanks a lot for the introduction. So yeah, my name is Giovanni, and today I will talk about containers. That's pretty much what this is about, with a specific use case, which is distributed machine learning, distributed AI, so to say. Let's start with a bit of an example, just to give you an introduction of the context where we place this work. But this work is not just limited to this context. This is just the main use case because we thought this was quite fun. This is split neural network. So we have nowadays in the literature, there is a lot of stuff enabling us to split these models, as you can see here in the picture, into multiple chunks. And then we can just deploy these chunks, these model partitions, into multiple machines and have distributed inference. This is quite interesting for very large models that do not even fit a single machine. So that's actually the only way you can deploy them. This is particularly interesting also when you are at the edge of the network and resources change very quickly. So you quickly want to adapt the model based on the resources you have available. And most importantly, you can now scale the single bits of this model independently. So it's quite convenient to increase the throughput of your model. But then the question is all of this is very cool, but what we focused is to answer the following question: how do we bring these model pieces pretty much everywhere, from edge computing scenarios to cloud computing scenarios? I will start by saying that there is no silver bullet to this problem. There are many solutions. You can use MLOps, you can use cloud storage, distributed storage solutions, volumes. In the paper, we go into a little bit more details about all the solutions. What we focus on is containers. Right now, if you notice, in the past few months, Docker is really pushing towards these Docker models, enabling you to distribute your models using OCI artifacts. OCI stands for Open Container Initiative, essentially distributing models via containers. So this was one of the main motivation, together with the fact that, developers are really familiar with containers. Everyone loves containers. Now we can distribute the code with our dependencies, and potentially we can put other stuff on top. We already do with binaries, drivers, all sort of stuff. But this is why we would like to use containers, but this is also a strong motivation against containers. Containers nowadays, indeed, they package a lot of stuff, much more than the original design was meant to. So not only code and dependencies, but again, all sort of stuff, which is also a problem because containers were not initially designed to have large files on top. So this might be an issue. It really depends. So there's a lot of engineering to use containers in such a way that you can use them efficiently. What we try to do in our work is exactly this. So we start from the fact that containers are definitely a useful resource for distributing code dependencies and other stuff on top. It can be a good use case for distributed machine learning, but what we need is something else. So we designed this 2DFS, which is a two-dimensional file system build and distribution framework for container. Our contribution are basically these three. So first of all, starting from the way container works, container image works, they have this design with multiple layers. I will go into details later. We designed a new layer type, which is called 2DFS field, which is a specific layer which is meant for big files, which, for example, the models, but it can also host your drivers, all sort of static files that are not directly connected to code and dependencies, but we have to distribute and store anyway. Then, of course, in order to achieve all of that, we needed a builder, which is specialized for this sort of big files, which goes beyond the traditional Docker build. And then we created a registry that takes this image, this new layer type, and is able to distribute efficiently all these blocks to your runtimes. And the main goal is to do all of this without changing the Docker runtimes or whatever container runtime you're using, because container runtimes are a lot. We don't really want to change the way Planet Earth works. So we are acting only at the registry and at the build time. Everything else must be fully compatible, so OCI-compliant. So every OCI-compliant runtime should work with this approach. So let's start with a little bit of introduction of how container work, specifically how the container image, according to the Open Container Initiative image spec, how they are composed. So we start from the file system perspective, always with this layer 0, which is the root file system. Think of it like the base of your container. If you're running a container with, I don't know, like Ubuntu 22, you can think of it like this layer 0. Maybe already Ubuntu 22 image has something like 6 layers. I don't remember by heart. But let's assume you start with something. And then whatever stuff you put in your container, what you do is pretty much adding layer after layer. And each layer is a change set of stuff compared to the previous layer. So if I'm adding a file, I'm adding a change set, adding this new file compared to what I had before. This is quite convenient because it enables you to keep track of changes and how the image evolves, but has the drawback that the layers are strongly interdependent. So also the way you build the container is affected by that. All we did is simply we introduced this new layer type, which is 2DFS field. Then, as you can see from this image, this is just another layer at the end of the day, right? But if we take a look from a different perspective, this is actually slightly different compared to the other layers. So this is why we call it 2D. It's basically two-dimensional. And what this layer is a sparse matrix that organized all the files into these blocks that we call allotments. And each allotment, bear in mind this definition because this will be interesting later, is a self-contained, non-overlapping, and independent file system space. Long story short, all the files in these allotments are completely independent, which brings the property that all of this can be built in parallel, cached independently, and distributed independently. So, for example, in my file system, I would like to organize this in such a way that I can contain different splits of my model. So I can organize a bit of this. We can think of it like a table holding a model split, and then another chunk of this holding another model split, so far so forth. But then I can do also additional stuff. For instance, I can put my NVIDIA drivers on a specific bit of this area. Because why not? And then also the network driver, so I don't know, like network daemon that I might have to run inside my container. So all of these sort of independent bits can fit different areas of this space. And the cool thing is that then at runtime, I can dynamically decide what I need, what I don't need. And eventually, if I'm running my container on a machine that doesn't have a GPU, I will leave the NVIDIA drivers out because I don't need that. Or if I'm running only the first split of my model, I just download that and I leave all the rest behind. So going back to this two-dimensional representation, we can think of it as this sort of a table. So we pretty much organize this two-dimensional space in rows and columns because this is very easy for humans. Potentially there can be other sort of geometrical solutions that we can imagine. We started with this sort of grid rows and columns because it's very human-friendly and easy for us to imagine how to organize the bits and pieces inside that, because at the end it's up to the developers to organize this space. And this is implemented as a sparse matrix, meaning that whatever area I'm not populating in this table, I'm not paying for it. So we can organize the space the way we like. How do we build these 2DFS images then? We wanted this to be extremely familiar for developers. We don't want to reinvent the wheel or anything. So developers are very familiar with Docker build. So this is literally TDFS build. We only changed the name. We start from a base image. In this example, I'm starting with Ubuntu 22. And then we have a target image, so the image name of the file that we would like to use for the finalized build. And what we provide is this file, this descriptor, which is a JSON file. And this JSON file effectively contains just the primitives for source and destination of the files that we would like to put in the file system. It's exactly like Docker add command, if you think about that. On top of that, we are just adding the primitive to select a row and a column where that file is going to end up. So I only have to take in mind and keep track of the row and column where the file will be placed in the destination file system. This has some interesting properties because, first of all, these allotments, as mentioned before, they are completely independent. So the entire build process can be parallelized across these allotments. We have some specific optimization in the caching system. For that, I would invite you to take a look at our paper. But the cool thing of all of this is that all these blocks are independently cached, meaning that if, for instance, I'm putting my model spread across all these allotments, and I'm updating a specific part of my model, I don't have to recreate the entire container layer, but I pretty much cache all the allotments that I can, and I'm only rebuilding the specific allotment that got hit by this model update. So this gets quite efficient if you have frequent model updates, which happens. I mean, in our paper, we have intensive discussion about this specific use case. But it's also interesting if you have a lot of binaries that you package in your container that have a different life cycle compared to your application. This is often the case for analytics applications that run on the side of your app, and we package all of that together because, yeah, it's convenient to distribute containers like that. Okay, now we know how to build this stuff, but how do we distribute this? Because again, we wanted to make this fully compatible with pre-existing runtimes. So we needed actually to change a little bit the way the container registry work. So we started from the official distribution spec, the OCI distribution spec registry, and we simply added compatibility with, first of all, this 2DFS field layer, this new layer type. And then we added this layer flattening capability. Maybe it's much easier if I start with an example, right? So this is our image. It's composed of all the traditional layers. And then on top of that, we place this two-dimensional file system. Now let's say I'm using Docker and I want to pull the image. So I will use the traditional Docker pull command. You will see at the very end of this image, we have this --1.0.2.1. And this is a semantic tagging system that we introduced that the registry is able to understand. This is enabling us to select specific rows and columns of this file system. So for instance, if I want to split one of my neural network and I only want to download that, I pretty much select the row and column from row and column 2. So in this case, I'm just selecting the stuff from row 1, column 0 to row 2, column 1 with this semantic tag. And the registry will take care of figuring out what that means. And what the registry does, takes these allotments, the ones I selected, performs this layer flattening, and then attaches these new layers on top of the traditional layers of the original image. So what I get back as a Docker runtime is a fully compliant OCI image that I can run, so I don't have to change my pre-existing infrastructure. So everyone's happy right now. To evaluate how this works, if this works actually, how we did was very simple. So we had a build infrastructure composed of a very beefy machine on the left, and then we had a container registry with this new registry with this 2DFS extension. As I mentioned before, the main use case for us was this distributed ML. So we started with a model zoo of 14 models. We split those models from 18 up to 82 splits, depending on the model size and the characteristic of the model. And then we tried to actually build these images first by using traditional Docker build, where each split is actually assigned to a specific layer, so in this sort of a serial manner. And for 2DFS, instead, we create the same thing, placing each model split into a different allotment of this two-dimensional file system. Of course, there's going to be more details about this in the paper, but long story short, actually, the build is quite faster. The reason for all of this is that, as I mentioned before, these allotments can be built entirely parallelized. So if I have a very beefy machine, like the one used for this experiment, I can fully utilize the hardware to parallelize the build as much as possible. And this will be, the gap will be higher and higher depending on how big the model is. So we have an average of 56 times faster build time for these models that we tried, with a peak of 120 times faster build time. Yeah, but again, the results might change a little bit depending on the hardware you have, how much you're splitting the model, model size. So this is pretty much an average. But what you can see is that this 2DFS is that line at the very bottom. The build time is quite static, no matter how much do we split the model. And the reason for that is, in this case, we are just creating the image once, and we pretty much contain all the splits. While for Docker, we actually have to create different images based on how many model splits we have to incorporate. The number of combinations of Docker images that you have to create is quite high, while with 2DFS, you create it once and you're good to go. There is also another use case, which is caching. So again, model updates, you can update stuff, not only models, it can be drivers or whatever. And depending on where the update happens in traditional Docker images, you can have different caching capabilities. So what happens in the traditional Docker build is that if you change something at the very first layer, you're pretty much invalidating the cache of all the layers above, because you are invalidating this change set chain. While in 2DFS, in this case, if you're changing an allotment, all the surrounding allotments will be preserved because you are not validating their cache. So in this case, we have two experiments of model updates, model retrain. One where we retrain only the layers that were at the very top of the hierarchy. So for Docker, it's sort of the best case. And one where we did the opposite. We started updating the model from the bottom layers, the ones stored in the first layers of the containers. And on average, we have 25 times better caching efficiency for 2DFS, while up to 75 times better caching efficiency for the worst case scenario of Docker, which is kind of cheating, but I mean, this stuff can actually happen in real world. So yeah, wanted to include that. This doesn't come for free, so this is important to keep in mind. And the issue is that this flattening technique that happens at the registry is actually an operation that we have to perform every time someone is requesting this model partitions. So this means that every time we have this request, we have this 2DFS that we have to convert into traditional OCI layers. And this comes at the cost of 20 milliseconds overhead for what we measured. There is also some CPU and memory overhead. For that, take a look at the paper. But yeah, this doesn't come for free. On the opposite side, on the other hand, I mean, the download time is already in the order of seconds. So 20 milliseconds, most cases, may be something worth paying for. To conclude, we also tried this in a distributed setup just to prove the fact that we can use this approach for distributed ML. So we created a setup with 10 edge nodes interconnected via gRPC. And we tried distributing a mobile net model with up to 10 splits across these different devices. And the results are pretty much what you would expect. The more you split a model, the higher the end-to-end latency is going to be, because we have additional networking overhead, but the throughput increases also. And the good thing from the container perspective is that for 2DFS, we only had to build the image once with all the possible splits. And then at runtime, it was a scheduling decision what to put where. While with traditional Docker containers, we had to pre-build all the possible images containing all the possible splits, depending on how many nodes we had, and then distributing the images afterwards. This concludes my talk. You can find here a QR code with this points to the website where you can download the builder. You can actually download the registry and deploy the registry on your own. Contributions are welcome. All of this is open source. And most importantly, if anyone is interested into helping us hosting this 2DFS registry for public use, let's get in touch, because I couldn't do that before the conference. And yeah, that would be nice. Yeah, that's it. Thanks.